To briefly summarize last time, we started talking about process level issues in fuel cell engineering. In particular, I mentioned that there were two major issues that tend to come up a lot. And one of them we talked about last time was thermal management, particularly in SOFC systems, where basically all the thermal energy generated by the stack has to be removed by excess air. And that impacts everything about how the whole flow sheet of our process works. We'll come back to that, especially when we're talking about carbon-based fuels. In proton-based fuel cells, particularly polymer electrolyte fuel cells, these are based on a polymer membrane. And I would say thermal integration is less of an issue in this system. However, the morally equivalent complication that we have to deal with in polymer systems is water, and how water is managed within the system. It has a huge impact on both the durability and also the performance of the fuel cells. Before we can deal with that at the process level, I need to give you a little bit of information about how the polymer membrane in a PEFC works. Many of these systems are based on Nafion. That's a trade name of DuPont. It's a fluorocarbon polymer, which also has a high water content. It's a bit like the materials that are used for contact lenses. It's highly hydrated, has properties of a solid, but also many liquid-like properties, and in particular, conduction of protons. The way Nafion's structured, it kind of has these PTFE-like regions of polymer. It's kind of like Teflon, but within that structure is this pore network filled with water when you hydrate the membrane. These regions are very tiny, on the order of the Debye length, so we're talking about like 30 angstroms or something of that nature. Within the structure and the formulation of Nafion as a polymer, it has these negative sulfonate groups that kind of protrude into these hydrated regions, and the compensating ion for the sulfonate groups is H3O+. So you can think of a little bit like sulfuric acid. It's almost like you have a solid sulfuric acid in which all the sulfur groups are bound to the polymer backbone, unlike a liquid acid where both the positive and negative ions can move around and only the protons can move. We are relying on proton conduction, which is a movement of the protons through the liquid solution. The properties of the material are very sensitive to water content. If you dry the membrane out, the protons become immobile because they no longer have a way of easily moving around within the structure. People have argued and have done a lot of calculations to figure out, well, how do the protons actually move? There's a lot of evidence that it doesn't move just by ballistic motion of H3O+. You can also have proton exchange process where one H3O+ gives up its proton to an adjacent water molecule, leaving it as a water molecule and turning the adjacent water molecule into an H3O+. So this proton can hop as a proton, which has a higher activation energy than you would expect if you just had traditional ballistic motion of H3O+ as an ion, although both are believed to occur. If we think about movement of protons through the fuel cell as H+, with those H pluses as they go through, you're either moving as an H3O+, or you're moving as a hydrated entity, which carries with it some water. Either way you want to think about it, the H+ drags water with it as electroosmotic drag. Speciating in terms of H+, we're dragging H2O along with our H+. Now, of course, as we do that, you think about if this thing's at equilibrium, you start out with a uniform concentration of water, and you start conducting protons are initially are sort of stuck at the same concentration everywhere because of the sulfonate groups. You start dragging protons across under an electric field effect. Those protons are dragging water with them. That actually sets up a concentration gradient where you dehydrate one side of the membrane and you overhydrate the other side. That then creates a diffusion gradient because now you have more water over here than you have over here, and the water starts to diffuse backward. And so there's also, at the same time, a diffusion flux too. The water is being dragged along this way with the protons, and then there's also, at the same time, this back diffusion of water. It is a complicated set of things that are going on. People have spent a lot of time modeling that. But the bottom line, and when we sort of think about this at the engineering level, people will try to characterize that as an overall ratio of the number of water molecules moving through the membrane per proton. There's a paper written by Springer about this subject, and he defined this quantity beta. Beta is the flux of water divided by the flux of protons. And that number is sort of in the neighborhood of 0.2 to 0.3. If we think about the practical consequences of that, we have a cathode where oxygen is reacting with electrons and protons to produce H2O. That's at one side. And then at the other side, at the anode, we're taking hydrogen to protons. So nominally, if we just think about the stoichiometry of this reaction, there is no consumption of water at the anode. There is production of one water molecule at the cathode. But at the same time, we're conducting protons across this membrane. And as those protons move, they are dragging water across. So even though there's no water consumed at the anode, for every proton that is being passed through, we're grabbing a water molecule and we're pulling it through. And then at the other side, we're producing one water molecule, but at the same time, two protons have gone through and they're carrying with them water. And so we end up consuming water at the anode and producing more than one water at the cathode. If beta is a constant, let's say it's 0.2, we're basically going to consume 0.4 waters at the anode, and we're going to make 1.4 waters at the cathode. And so not only do we have to worry about the production consumption of the water by the reactions, we also have to worry about this additional transport effect of water. And this all feeds into our material and energy balances. When we go to design the whole system, we have to manage all this water. If we don't, one of the consequences is we could dehydrate parts of the membrane and deactivate it or even destroy it. Alternatively, we could end up with so much water collecting, particularly at the cathode, it can all precipitate as liquid water. And then that liquid water blocks access to the gas, and the oxygen gas can't get to the electrode anymore. And that also deactivates the cell.